because never a good time when I forget that. I am going to be uploading this to YouTube afterwards, so that we have a copy of this for all time, because Twitch does record this, but they also delete those recordings after 14 days. So not necessarily best for archiving. Anyways, Stu is also a part of our wonderful community in Denver, um, and you've been working on some really interesting projects with Rust, Stu. So I'm super looking forward to seeing this. So without any further ado, I'm going to hand it over to you, Stu, and take it away.
Cool. So I'm going to go ahead and start out introducing myself. My name's Stu. I've been working in Rust for it was probably the past 4 years or so. I was the director of engineering over at ThreatX. We were using about probably 80% Rust in our WAF, a lot of the back end. We were at the time that I left, we were phasing out a lot of our older Python code base and replacing it with more Rust. Um, I've since left then. I left at some point in the summer. I've recently joined a company called Randori. We do offensive security, basically automated red teaming. We're red team available to hire. You bring us in, we're going to watch your perimeter, see what shows up. We have a really cool recon tool built to be able to see, to discover assets that you have, understand them, understand where your risk lies. And then we have a red team on staff that once you authorize things, we will go after it. We'll exploit it. We'll see what we can do, see how far we can push into your department to help kind of train your defensive team, help them learn. We show them what we did, how we did it, how you can improve. So I've been brought in to help on the attack automation side. So in my past, as I mentioned, I had a lot of embedded systems in the past, and before the company that I was at was very much blue team. We were building a web application firewall. So, and I have done pen testing in the past, like really just focusing on finding problems, exploiting them, and writing summaries of how I did it. But I've never really focused on, okay, I've exploited this. Now I want to persist, or I want to start moving laterally through the network. Like normally my scope was pretty narrow of like one service. And I'm doing a lot more of that here at Randori, of like kind of looking at this larger offensive role of like, looking at an entire company where a lot of different paths are available to us. Like, yeah, we can start phishing users and use that to get a toehold. Or yeah, we're going to want to be able to get an implant on a device and start using that to start kicking off exploits in other parts in their internal network. So I really wanted to learn more about like writing malware. So I decided, okay, cool. I'm going to write one from scratch in Rust. And let me share my screen. Um, and so, yeah, I picked this project up to do it. People write implants, and like, so an implant is a special kind of malware that you're usually using post exploitation, like I said, to get persistence on a box. So like, I've broken in the first time, but maybe I don't want to do anything else yet. I want to come back later. And maybe that same exploit's not there, or the same path that I got in. So I just want this to be able to get me a toehold so I can stay in there and come back later. Or if we're moving on further, and like let's say we get kicked out in another part of the network, hopefully we can go back to this, previous implant and kind of relaunch our attacks. There's a lot of them out there. There's open source ones online that you can take a look at. You see them written in a lot of different languages. C is a really, really common one, but there's ones written in Python and PowerShell. There's a fair amount of Go ones. There's a really popular Java one. They're really in a whole host of different languages. But from what I've seen, C seems to be the dominant player. So in a lot of what I'm going to be talking about, I'm going to be comparing Rust to C. Like, is this easier? Is this harder? Is this cheaper? Is this as capable as if I did this in C? And I think one of the best ways to kind of like start off in this is to pick a implant that exists out there in the wild and start talking about that so we can get used to some of the terms in it, how they work, the way people develop them. And luckily, when I started out on this project, about the same time, uh, the NSA released this like really great document. They had gotten a hold of a GRU written implant and rootkit, and they documented like absolutely everything about it. They just like tore it apart in a way that I wish like my coworkers would document their code. Everything about the C2 method, like how how the implant works, how it's designed, what libraries they're using, all the way back to, and this is when it starts getting really interesting because this is kind of a dry technical document, but they keep going back and start talking about like what is the network, the Russian controlled network of like this command and control side look like? How are their databases configured? So it's kind of interesting because it's obvious this isn't just something they like found in doing incident response. They either somehow took control of the source code for this project or they infiltrated a Russian network and started documenting the internal. So it's this cool kind of like big old intercontinental like middle finger from the NSA to the Russians. So um so like I said, they documented this pretty extensively. They dubbed it a word that I'm not going to try and pronounce. It's apparently translates to like roughly to like wood chopper or to chop wood. The reason why they named it that is they saw references to this word inside the binary and throughout it. So in the documentation, that's how they refer to it. From here on out, I'm only going to refer to it as either the implant or like the individual parts of it. So we'll start looking at these individual components. So there's four big parts of it. There's the client. So this is actually what goes onto the compromised system. Um, there's a kernel module, which is basically a rootkit. They they're obviously an extremely well-funded and very talented team. So they're able to build like a really powerful rootkit kernel. And this is for like most Linux-based systems that it will go in, you're able to declare like files to start masking them. So if someone runs ls, this kernel module that they load in will actually interrupt that and scrub out any kind of files that they've decided to hide. It does a lot of the same stuff for network activity. This is like a really powerful, very expensive thing to do. This is not something that I'm going to like some dude in his free time on nights and weekends is going to be able to implement. So definitely out of scope for what I was working on. Um, so next they have a tool called the agent. This one was kind of interesting in the documentation that the NSA produced. It mostly looks like it's a helper function to help set up VPN connections and like file transfer and other things like that. It looks like it's mostly there for convenience from everything I read. Um, and then finally, the command and control. I'm often going to be referring to this as C2, command and control. It's a pretty common term for it. Theirs they implemented, it is using an open source WebSocket implementation. It's in C++. When the implant comes up, it's going to phone home to the C2 server. And they've got, once again, like I said, the NSA does such a great job of tearing apart exactly how this works. And they don't get into a lot of the whys they were doing it, but they get into the details of it. So when this implant's sent out into the field, so if you think about this, you're writing malware, you can't like include like a configuration file along with it, or like, you know, a lot of the nice ways that we're going to configure software for a system that like means to have it deployed on there, like, you know, put your configurations through envs. So they actually bake a lot of the configuration into the binary itself, either through a build step of it's included in the source code somewhere, Or a more common way that they're going to do it is they have a bake process that will actually go in and manipulate the binary itself and write in the configuration values. In the documentation, they don't make it clear which method this implant uses, but they do talk about kind of what's baked in there. They're going to bake in a public key for the C2 server, a username and password to be able to connect back to the C2 server, and then where to find it. So obviously a lot of this stuff you're going to change per depending on the attack you're doing, like who you're exploiting, or you're going to be using multiple different C2 servers all within like the same network. And this process, it's going to come back, it's going to connect, it's going to say hello, it's going to provide some of that information. They do a negotiation, and eventually it is given a like unique token, which is then baked back into the implant. So once again, not going to dive into the details, but now that they have that connection set up, they've got a WebSocket connection back to the C2 server. C2 server has some unique credential handed back to the implant. They decide they trust each other. Now it's time to cause trouble or not cause trouble for a while. So once you get, I should pause here and say, if anybody has any questions or like want elaboration, like please feel free to speak up. Like I would like this to be like interactive. And I'm also going to let you know, like I'd mentioned earlier, I am not an expert in writing implants. So there may be some things, because this is baby's first implant. There may be some things I don't know, or I can say this is what I've seen so far in ones that I've looked at. But so implants up, it's connected. They decide they trust each other. And at this point, you may decide, hey, we're just going to leave it for a while. We're going to sit. We're not going to do anything. We're going to wait until we get our orders to do something. Or, cool, let's start causing trouble. In this example, in this malware, they provide like a fairly low level series of commands back that the implant can handle of, and like this is really useful because sometimes you don't really know what trouble you want to cause until way down the road of like, oh yeah, I really wish I could do X or Y. So a lot of this stuff is implemented in pretty low level stuff. So then the attackers on the C2 side, they can, program out whatever they want, and they're provided, what looks like fairly low level controls. Like some of the stuff we're looking at, it probably looks familiar to like, read a file, write a file, open it, close it. You can string it up and you can probably do most of whatever you want on the system.
Quick question.
Yeah.
Can you go back to that diagram that showed the networking?
Yeah.
The victim's computer. Just looking for.
Yeah. Let's
clarification. Yeah, that one.
Yep.
So I see. So on the left, where you say actor controlled infrastructure, I see. I kind of missed that. So that's where the hacker server is running, and it's connecting to, I guess, the victim. Maybe you could describe like where
Absolutely.
each of these physical servers might likely reside.
Totally. That's a so yeah, in this situation, so let's say I discovered you're running like a old out of date version of I don't know, like WordPress or something. We're going to have some kind of attack that lets us run arbitrary commands. We get in it, we get enough that we download the client, the implant itself. It's going to be placed somewhere. It's got that configuration. If we're able to, they provide this kernel module. So this has this extra hiding capabilities that I'd mentioned. It also, if I remember the documentation correctly, if the implant is removed, the kernel has a way of, the kernel rootkit has a way of restoring it. So then the client is going to phone home back to the server. Because often when you do this, you're going to have like an egress, but not necessarily an ingress to the network. Like let's say, this is your, like we've exploited someone's like desktop PC. Like chances are you're not going to be able to like route just straight through the firewall, and there's like an open port to like connect to this person's PC. So we want this thing to be able to connect back to our internet exposed infrastructure. So that's when it's going to look at its configuration inside its startup and say, okay, where's my C2? Where am I connecting? And so these are going to be in any number of places. So and there's different ways to do this. They could have these directly exposed, or they could have some, because like, we're not going to have this implant phoning in to like some Russian controlled IP. So either this server is going to exist somewhere that is like not looking suspicious, or it's going to be routed through, you'll have some kind of proxy to redirect the traffic of like just some EC2 instance somewhere, redirecting back to, now this is actor controlled infrastructure. So this is on their network. They have control over it. They're able to connect directly to it, do whatever they want. And like I said, that agent is just there for, like, let's say I want to initiate like a file transfer to like push a file in there, or I see that they have stuff like I want to start pulling backups off the system, or whatever else. That's there to help facilitate that. One other thing that it's used for, and I might be getting into this later in some of the slides, is often you want to have the ability to create like a VPN connection into the network. So like, I'm the GRU. Once again, I'm really well funded. I got a bunch of really cool 0 days laying around. I'm not going to just like drop them in to someone else's computer. You don't want that valuable stuff to land on disk there, because then someone's incident response can discover it. They're going to know what exploits and what capabilities you have, and it's going to go get patched. So like, you want to do whatever you can as an attacker to keep all your like the pointy end, the exploits, over on this side in your controlled network, and then somehow route your traffic through the implant so you can attack other computers on the network. Does that make sense and help clear that up?
Oh yeah, that added some more context and filled in the missing pieces for me. Thanks.
Awesome. Yeah, and once again, the calling out of the MySQL, that's just another one of those, like, it's like, man, they really were deep into the network, that they knew exactly what they're running. And like I said, they have the configuration of like how they're running MySQL on the like Russian networks. I'm like, that's pretty cool. So and we get into, this is just, a lot of the file operations. Like I talked about, maybe you're going to want to start exfilling stuff out, like pulling off backups if you find them on a system, or start pulling all the contents of the database if you're able to, or you want to start like rewriting configuration files. This should give you, whatever you're going to want to do. File upload and download. So like I said, this really is probably going to kind of look like a C program of file open. We hear back that it was successful. I want to read data, and then it's going to send back the read, and then it's going to close it. And so, we won't dwell on that too much, just kind of knowing that that capability is there, and you generally want to keep it really low level so you can be really flexible. It's something that I've learned with the team that I'm working with. They're really, really creative people. They find abuses and misuses of computers that I would absolutely never predict. So I'm learning really quick, like, keep these APIs very, very low level, because these attackers are going to want to do something really, really strange with it. And I want to give them the flexibility to do it. So yeah, this is just another example of why that's really useful and how other people are doing it. So yeah, and this is a chart showing like how I would want to, how I was mentioning earlier, if I've got exploit code on my system, I don't want to deploy this on someone else's like network where incident response can discover it. Or I'm not going to want to drop, I don't know if any of y'all are familiar with, like, there's a bunch of open source tools like Nmap or things like that. If I start dropping that on a customer network, like a virus scan or some agent software is going to detect that and flag it as suspicious. So it's really best I run this. So, in one of those examples, it's going to be Nmap. I want a port scan. I've already compromised computer 1. I want to compromise computer 2 now. So I need to figure out a way to do it. So Nmap is a port scanner. Sits there and runs traffic against a remote host, poking each port, trying to identify, hey, is this open? If it's open, what's on it? Is this something old? Is this something I can do something with? So we're going to run that. It's going to route the traffic through the agent into the server, back to the client, and then the client is now going to take this traffic and play it against the remote host. And so then the port scan goes and hits them, and then I get the reply back and I see, okay, cool, is port 80 open or whatever. So that gives a very, very high level of how this thing worked. And I can send out the documentation on this. I can drop it in the chat afterwards. If anyone's interested in reading more on it, if that just like sounds like your thing. But that's the high level, and that's generally what we're going to want to do. We're going to want to be able to run arbitrary commands. We're going to want to be able to manipulate files and route traffic. If we get those, hey, we got a pretty okay basic system going on. Like there's a lot of room to grow and a lot more stuff that we can do. One of the things that I didn't cover much in here is anti-forensics. I did cover it that they have this really nice kernel module that lets them like mask traffic. But there's a lot of other signatures of like how a piece of malware can behave and what can like, flag the blue teams of saying, hey, this is really suspicious. We should shut it down. I did not look into much of that in this project. There's that is a wide and deep field. I really just kind of wanted to get something basic working. So I won't be able to answer a lot of questions on anti-forensics, but that is something deep, and that is something that they go in to quite a bit in that paper. So cool. I want to talk a little bit about why I wanted to do this in Rust. So like I'd mentioned a while back, I took a job. So we're going to go all the way back. This feels like the long ago. 2016, I took a job at a company called ThreatX. They were writing a web application firewall in Rust. At that time, only the WAF itself was in Rust. It was a Nginx module that would be loaded in, and they decided to write it in Rust because it was just easier to do that than work in C, and most high-level languages were off the table. When I joined, I was really skeptical. Like I wasn't sure if that was really the right tool for the job. I'd written a little bit of open source Rust for fun. I really liked it. I really hate C. Like for a guy who's written as much C in their life as I've written, I really dislike that language. Maybe I dislike it because I've written that much, and it's just like I'm over it. I don't want to sit there in GDB and Valgrind trying to find some stupid mistake that I had made. But yeah, so I joined, and I'm like, wow, is this really the right choice? This language seems really immature. And really quickly, I found out, no, this is like a really good choice. This language is great. It matured while I was working there too. So like when I first joined, like CERD didn't even really work on stable. Hyper wasn't a thing yet. Like we were doing a lot of web requests using like libcurl. And it just kept maturing and getting better. But what really stood out to me, even if the ecosystem wasn't there, a lot of the tools to raise the quality of our code base was. Rust provided a lot of functionality to help us write more faster. It helped us more quickly write high quality code that we could trust. And like we found that our velocity in general like improved a lot. And it's not just the language itself, like the ecosystem around it. I find like writing unit tests is just a lot easier in Rust than it is in C. Like with C, I usually find myself like getting into some like weird pattern to be able to write like good decoupled code. And it just looks kind of crazy. Where Rust, it feels pretty natural, and I can make like high quality, testable, and still performant code. Um, the documentation tool is just like, it's so much better in the C world than in the C world. It's really easy. Like I'm sure a lot of y'all have already seen, like, Cargo Doc, it just works great. It makes it really easy to document my code, so I don't have an excuse to not, because like I'm lazy, and I'm chances are going to skip that if I can find a reason. The static code analysis, not just built into the compiler itself, but like Clippy's, like generally like really high quality. I found like really good performance bugs and a couple correctness bugs with Clippy, but like what's built into the compiler itself is generally a lot better than what I got out of any static code analysis tools in C World, which is just, oh, it's so nice. And you always hear a lot of talk on the internet about like how fast Rust is, and that really, like, that's nice, it's cool. Generally you don't need that much performance. I really think like quality is the #1 selling point of Rust, and I'm able to write higher quality, better testable code, not just comparing it to C, but generally compared to like my Java. I feel a lot more confident with it. And also, since like in C world, I I often tried to get into fuzzing, and I had a lot of trouble with the tools, getting them to work. It was generally just a pain. And my first time I ever tried to do any fuzzing with Rust, I found like a good high quality exploitable denial of service on a popular Rust package within like, I think it was at the coffee shop for like an hour. And I like had that bug report ready to go. And I'm like, this is awesome. And it's not even just one fuzzer. There's 3 high quality ones that I switch around with. And it's so nice to be able to bring that into my code base. And like, I don't have to put out a lot of effort, and be able to get good machine driven testing that's, it finds a lot of really dumb bugs, like things that are like, okay, I probably never would have hit this in real world use cases. Every now and then I'm like, oh yeah, no, that's genuinely exploitable, or that's really nasty. And the cost is so low that it like really helps with the benefit on there. And also the prop testing. So this can give you an idea of like the sick mentality I have. When I first decided to learn Rust, my Hello World was actually a implementation of the Murmur 3 hashing algorithm, just because I'd done something with it at work recently. I needed to compare 2 different file systems to sync up the differences. I ended up using Murmur 3 for reasons I could not tell you now. I don't remember. And like I did that all in C. I thought that was fun and cool because it worked really fast. I'm like, yeah, let's see if I can port this to Rust. And I didn't really know what I was doing. I implemented something over a weekend, and it worked. And I posted it online. And then like somehow like people started using it in production. I'm like, oh no, oh no. But I didn't think much of it till I got a bug report. Somebody was using it in a distributed database, and it had like a really embarrassing bug in there where it wouldn't handle, um, it was characters over 127 bits. It wouldn't handle them correctly, and you would get the wrong hash. And it was like so mortifying to me, because like I can't imagine how hard it was to debug that problem of like whatever crazy distributed database problems they have. For some reason hashes aren't lining up correctly. They have some high level bug. Oh, the hashes aren't correct. Oh, it's because of this like sketchy library some dude wrote in a weekend. um and so like when they got that bug report, I was really mortified, and I wanted to make sure it didn't happen again. So I picked up, Rust once again has really great prop testing tools. So I was able to set up a prop tester And it was my first time using Rust BindGen, which once again, another really great polished tool. Pulled in the C implementation. I was able to wrap it with BindGen, and then used a prop tester to, it would generate a random input. It would run it in my Rust code, it would run it in the C code, compare the differences. Cool, they match. Let's do this 1,000 times with 1,000 different inputs. And it gave me a lot more confidence of like, hey, yeah, this is actually high quality code and this is good and people should trust it. So, yeah, and I know these things exist in other languages. It's just they're so dead simple to use. And like the Rust community prioritizes it and it really cares about it. And so like they're generally just really well polished and really feature rich. So another thing with the quality is like no nulls. I'm not gonna like harp on this too much because I think a lot of people here are on the same page. It's like I think it's like bonkers town that we're still making languages that have the concept of nulls. But I'm really glad Rust doesn't. It makes being able to use option and result instead of like, oh yeah, here's the result, or maybe it's 0, better remember to check it, is like really nice. And it makes code easier to read. It forces me to handle errors. And it just generally improves the quality of the code, and it pushes my my effort forward. It makes me handle errors now instead of like, oh, I didn't handle it. Oh, this issue ran in the field. Like I ran into this issue in the field and it crashed. And so here's a reason why like this is quality is especially important in writing an implant because like, you know, let's say we spend a ton of effort. We wrote some actual 0 days to be able to break into a perimeter of a company, and then we land an implant on it, and you know our 0 days are burned. We're not going to be able to do this again. They've patched this system, but cool, we have an implant on the back end. And now, like, because of my sketchy code, it crashes on startup because, like, oh, I forgot to check this return. Now the implant's dead and we can't do anything. And we just wasted all that time and effort and money. So it's like, it is absolutely crucial that once we get something on a system, it does absolutely everything it can to phone home and keep phoning home and keep that connection up and like handle crashes and handle them gracefully. Because yeah, it's not as easy as just, oh cool, it's SSH in and just reboot the service. It's often not an option here. So I kind of covered this. I think this is a positive, but it's not like a soaring like, yeah, they're doing a great job. It's a fairly decent ecosystem. It's growing. It still is a really young language. Like every now and then there's something that I hit that I'm like, oh man, I really wish I could do X, but I can't because like it's just the driver doesn't exist for it. And it's getting better. I remember a while back I wanted to use ActiveMQ in a project, but I wasn't able to just because there wasn't AMQP 1.0 driver that existed. There is one now. So like this is just an example of how things are getting better, but it's still, this stuff's young and it's, there are bugs in it. Like while I think it's easier to write high quality code in Rust than a lot of other languages, there's a lot to be said for just a lot of time and a lot of developers beating their head against the wall, and that shakes bugs out. And I have found fairly nasty bugs in fairly common libraries. I think one of my favorite ones was I found a bug and I wrote an exploit for it for a WebSocket implementation in Rust where you could get it to accidentally send you messages that were meant for other clients if you were able to time connecting and disconnecting correctly. And it's like, okay, totally understandable that landed there, but this is just a sign. This is a young ecosystem. There's bugs in there. But yeah, generally you can find what you want. And if you can't, like I'd mentioned before, Rust BindGen's there for a lot of this stuff, and especially in writing exploits. Well, a lot of the stuff I want is like C code or C libraries, so I can just pull in the C library. It's a little bit different on like the server side stuff. So when I first started this project, I really wanted to do my first pass of the command control. I wanted to do it over ICMP. So ICMP or ping allows you to attach like a small amount of data on it. I don't remember how much off the top of my head. I think it's 4K. So you can actually implement a complete command channel over just ping. And there's a lot of crazy stuff on the internet. You can see people have built like VPNs using just ICMP. So that was the route that I originally went. And I was like, yeah, this is going to be fun. I didn't find any ICMP libraries that really scratched my itch. So I was just implementing it with like libc, just directly like I'm working with C. And like it was going okay. It was kind of slow going. And then I'm like, you know what? Let's just step back. Let's get everything working beginning to end with an easier to work with C2 mechanism. And then I can switch this out later. Like because my goal too, long term, like, if I implement ICMP for my first C2 mechanism, I'm probably also going to want 3 or 4 other ones. Because like I'd mentioned before, if we get this thing on a network, we want to do whatever we can to get back to that C2 server. It's crucial. So often you're going to see um, implants implement multiple different C2 mechanisms. So I mentioned ICMP, that's a popular one. Doing it over DNS is a really common thing. Straight up TCP connection over TLS, UDP, and you want to be able to rotate through all of these. So like, okay, we're going to try TCP. Cool, that didn't work. Let's fall back to something else. Let's keep falling back until we can find something that does work. So yeah, big rant on that. I wanted to have multiple. I started with ICMP. It was a pain. So I'm like, you know what? Let's just make this really easy. I'm just going to use request, just straight up HTTP. This is a huge library and there's a lot that comes with it, but you know what? It works. And like, it turns this thing that was like a couple day week task to like, yeah, cool. I'm done in an afternoon. Let's move on with our lives. And now I can go back. So this gives me the opportunity to do like really rapid development, act like I'm working a high level language, and then later, cool, I want to optimize. I want to do this really low level ICMP stuff. Where if I was writing this in C, yeah, I'm in C world no matter what way I'm going. Like, yeah, I could use this higher level protocol, but I'm still working against libcurl and it's still slow going. And I can't do these like really fast iterations of saying, hey, I don't care about performance. I don't care about file size. Um, so it's really nice because it just gets me a working product. And often I've found I will sometimes get really focused on like performance or something like that. And then you implement your first pass. Often the performance is good enough. It's okay. You don't need to worry that much. Come back later and tune it. So I talked about this a little bit before the streaming started. Cross-compiling sucks less with Rust. It's not super great. I'm super stoked about that tool that someone posted. So I'm going to look into that to hopefully make it even better. But yeah, I remember early on in my career, I worked on a project. We targeted a ARM7 with no MMU, and it was running UC Linux. And so like we'd have to build our own tool chains. You couldn't just like app get one. And like we would have to build them, and it was such a pain, and everything was just like really fiddly and terrible. And like, yeah, there's like really cool tools like I think it's Cross Tools NG to help you build up your cross compilers. But even with that, it's still just like kind of a pain in the ass. But with Rust, it supports so many like targets and it supports them like pretty well. And for the most part, I don't need a lot of configuration to get them working. It's really, really nice. Like for an example, this is all I needed to do to target, and I'm pretty sure someone's gonna like call out, like I'm gonna say, hey, I don't know why I actually had to do this, and someone on in this meeting might know. I just have to install my cross compilers And this is the part that I didn't really understand. I have to tell Cargo, hey, like, please use my arm linker. And then I add my target and then just do cargo build with my target. I really don't understand why Cargo doesn't see, cool, we have an arm target, let's use an arm linker. For some reason it doesn't. You need this step. But like, if this was the worst of my problems, it's really not a big deal, and it works fine. And generally a lot of the like modern stuff is supported really well. So why not Rust? I'm going to try and be pretty honest about the ups and downs of Rust here. And I know this is like a very Rust centric crowd, so it's like, yeah, Rust all the time, but it's just like not a fit for everything. So first thing, like file size is a really big deal when writing implants. So, I described earlier our process of like attacking a system. Like, let's say this exploit only lets me write like 4K of a file at a time. If I've got like a 20 meg implant that I'm trying to load, that's going to take a while. Or maybe I have this on I have some weird sketchy VPN of somehow that we're connected onto this remote device. It's a big deal if I'm trying to push something really big. Or often embedded systems and IoT devices are like prime targets for persistence. So think about your IT staff. They're often coming through and they're patching on your desktops and your servers, but like, are they patching your like remote aquarium controller? Are they like, if you have like an internet enabled tea kettle for some reason, is that getting patched? How do you know if that's exploited? How do you know if there's something on there? You don't. And so like, if you can exploit one of these and get persistence on it, you're going to have persistence on the network for a really long time. And these embedded systems, they often don't have like a lot of room on there. Like they might have a like 20 meg NAND chip on there and like 19 of it's used because they're trying to save pennies. So like you really want to be able to get your executable absolutely as small as possible. So my goal with this, and there's guides online. You can do a lot of stuff to get Rust compiled size down to like really silly levels, to just a few K for a hello world. With each one of these steps, you're often throwing away features that are really usable. Like, oh, great, like I have maybe just a couple weird compile steps, or maybe I'm not using libc anymore, or maybe panics aren't there anymore, and you have to like trade off like, hey, what is worth it to me and what is just too much. And eventually you get down to, you just have libc with a slightly nicer language on top of it because you're using no std, but hey, it's 50K. So you really have to weigh that out. My goal for this project was to keep it under 1 meg. With using request, it weighs out at about 1.6 meg. And I use a few tricks to keep file system size or executable size down without any tricks of just like, okay, let's build it and like, let's be lazy. Comes in at about 3 to 4, which is, it's really way too big. Like that's unacceptably big in this world. So like I'd mentioned before, on one of the advantages, I can do this high level development and come back later and optimize for file system size, and I have, or executable size. I have these options. So that's nice. That's an advantage. It's still just really big executables. And it's like, this is not an interesting problem. This isn't what I want to work on, but it is a necessity. Yeah, its reputation to be difficult to learn doesn't come from nowhere. I like it. I think it was 100% worth learning. And I think it's worth learning for most people. But some people don't want to learn. And I don't want to force them to learn. So a long time ago, I worked on a project and I was brought in, I was an embedded system developer, And a lot of the work that we did was in PHP. And that team loved PHP so much. And they were some of the best PHP developers I ever met. They went to like weird levels of how much PHP we had. Like on that embedded system, a fair amount of the user space was actually written in PHP, and we would have like PHP user daemons. Um, but it worked because the people knew the language well and they knew how to work with it. And eventually, a we got moved. There's a reorg. We had a new executive and a new architect, and a mandate came down of no new PHP development. Like, you don't write serious software in PHP. And so they've basically forced everything to be written in Java and Scala. Scala got crossed off the list pretty quick because people are like, this is horrible. Like the code that you Scala code written by PHP developers is like especially difficult to read. But generally, people were really unhappy. They didn't want to learn it. There was a learning curve there. It was steep, and we produced lower quality code because of it, because people didn't want to learn the tools. Um, and that's the same thing here. Like, if you have a team that's not interested in learning Rust and they have a skill set in C or in another language, like let them work in that language. Don't force them to learn it because you want to introduce this language that you love. And then so at ThreadX, we actually had trouble hiring for Rust developers. Like we never found Rust developers who had a fair amount of production experience before. We generally like looked for just really smart people and trained them up. And because of that, we usually saw a couple month downtime of like, the person's learning, they're slowly getting up to speed. We had a shallow end of the code base where they could start slowly working up to more complex parts of the code. But yeah, that learning curve was real, and it cost money and it cost time. Um, yeah, and it was just really tough. And I remember at one point to kind of like try and like help this hiring process along, I was talking to a recruiter, and he wasn't finding anybody with Rust experience, and it was when we still thought that we needed people with Rust experience. And I was like, well, maybe like Scala developers, like that's the path that I got in here, and I'm like, maybe they'll have an easier time to learn. And he gave me this look like, hey, like if your bigger pool to fish from is Scala, you're in trouble because that's like a really small pool too. Um, so yeah, this stuff really impacts like a growing company. One thing that's interesting on this that I found out is like more senior developers tended to have a lot of trouble because they had a lot of preconceived notions of how programming languages work, or like this is how computers work, that were very baked in. Uh, we didn't have as much trouble with interns because like they didn't have a lot of this stuff that they had to unlearn. And there's like, yeah, okay, like this is the way computers work. Like ownership matters. I'll just learn ownership. Um, and it's just like, yeah, I don't know, it's just a rule that the computer has. So I thought it was really interesting that, they still didn't get to be as productive as fast. They still had a learning curve, but they just didn't seem to struggle as much. Cool. Does anybody have any questions on anything else about like the positives or negatives that I saw in Rust? Cool. So I am going to dive in to the implant itself. So like I'd mentioned, one of my goals was I really just wanted it to be under under 1 meg. I wanted it to be easy to work in. I wanted to be able to have simple file manipulation. I want to be able to have a remote shell to the system, and I want to be able to have a VPN that I set up to this remote network and can start doing things. I got a few of those. They're still on the to-do list. I have the remote shell set up. File manipulation's mostly there. The VPN is going to be like the big one that I'm actually like really excited to do. But that is to come. So I'd mentioned right now I'm just using request and HTTPS for my, or HTTP in this implementation for my C2 mechanism. And I'm going to start walking through parts of the code. And if there's anything that's interesting that people see and they say, hey, like, why are you doing it that way? Like, why not do this? Like, totally like speak up. I really do want this to be pretty interactive. So first thing that I did is all of this stuff exists inside one large Rust workspace. It makes it really easy to work with. So I've got my C2, and then I have a language that describes what this protocol looks like. So you're going to notice that I have to exclude my implant from it. So this is something that I hit early on that was kind of a pain, is there's a few optimizations that I want to use on the implant side that I absolutely don't want to use on the C2 side. But if something's in a workspace, they're going to have the same compiler flags applied to every crate inside it. And so I have to exclude it. And so it's built separately outside of the workspace, which is kind of a pain. I would love for them to fix that, but I also understand like this isn't really a priority. Like this is something that I'm running into. So, so we're going to start on the implant itself. So,
Stu, before you get too far in, I got a
yeah.
request to increase the font size.
Oh, thank you. Yes.
Stu, what ID do you use? Is it Sea Lion or is it IntelliJ?
It's Sea Lion. I am a huge fan of Sea Lion. And yeah, it makes working in the code really, really easy. I love how they annotate. So here, did that change the, I think that only changed the IDE font. Yeah, it did. Are there any IntelliJ gurus who know how to change the font size? Let's try this.
I think you just control zoom in or something. I don't know, like control plus.
Okay, cool. There we go. Is that better, or should I turn it up more?
That seemed to do it to me. I've asked chat, but there is a delay between when they see and when they can chat back.
Well, I'll ramble on, and if someone wants it turned up more, I'm happy to do it. Or if there's any other questions or anything. So, like I was mentioning, there's like a balancing act of like, hey, how low level do I want to go? Do I want to strip out all of libc to make this executable tiny, but like kind of a pain in the ass to work with? So I decided to start, pretty easy. Let this be high level. One of the first things that I tore out is panic. Like I'm never going to panic in the field. I don't want to be spitting out a stack trace for like incident response to see it if something goes wrong anyways. If it panics, I just want the executable to like GTFO. And like, I don't ever want to abort, but at that point, if I'm panicking, it's really my only option anyways, because I'm not going to be handling it or catching it. So this is something that I was like, yeah, that's safe. This is low effort. I turn op level Z. These next two are ones I generally put in most projects for my release builds. I turn on LTO and code gen units 1. Like they make the release builds like significantly slower. but the optimization is just like a little bit better. Once again, anytime that you are applying any kind of optimizations, before you apply them, you need metrics to say, hey, like, is this actually doing a better job? So being able to see, like in my case, I don't care about CPU or wall time performance because a lot of my actions are going to be happening over the span of like months or minutes with lots of weights in it, but I do care about file size. So that's my metric. So generally before you start playing with anything besides like the default production build, make sure that you have like benchmarks of like, yeah, is this actually making my build faster? Instead of just, or like my executable faster, is it just making the build slow? So one of the nice things I initially didn't want to build, as I'd mentioned earlier, there's often you're going to see a baking process where you have an executable and then you run some kind of script on it that's going to drop all of our configuration in it. Um, I played around with trying to do this with a proc macro, and I still kind of want to go back to it, but I was like, hey, let's just stop. Let's just use something upstream. There's a tool I found, a library called Configstruct. It lets you declare a configuration in a TOML file or a JSON file or whatever, and it's going to see that as part of your build step, and it's going to generate a Rust file. And so it's going to embed the configuration in there. I was like, cool, that works for now. I'll come back and make a pretty macro, but this gets the job done on what I wanted to do. Now in retrospect, and this is another reason why it's really nice to be able to just get it working end to end and then come back and not just like fine tune and get everything perfect. I realized, hey, that's a really bad idea. I don't want to couple configuration with build. So if you think about this, we used the example earlier of like we have these Russian attackers. Chances are their development and their attackers, they're different teams. Like they've got a development team and they got an attack team. Why give the source code to the attack team? They probably don't need it, and you don't want to have that stuff coupled together. So it's nice to have it as two separate steps. So in retrospect, I realized, yeah, this shouldn't be part of it. I should just do this like everyone else does, like some kind of Python script that writes it into the static space of the executable. But it was really nice. Another positive of Rust, it took what would have been like a hard job in another language to experiment. There's something off the shelf, and it taught me really quickly, yeah, it's not really the route I want to go. And it's as simple as doing that. We can look at our config.toml. There's really not much in here. There's other optional parameters, but really what I care about in here, so I got a callback parameter or a callback period, which is how often it's going to phone home. So like if I'm dropping this out in the field, I don't want this to be every 5 seconds because like someone's going to see that. They're going to see it in logs. Like, why is this thing so noisy? You're going to set it at a much higher number. I have it in 5 seconds just because this is local development. And I have a way, and we're going to cover it, to start manipulating these configuration files remotely from the C2 server. And we'll get into like why I would want to do that. So the other things it makes by declaring features, like I said, I want HTTP right now, but I'm not going to want it in the future. So I can make it a feature and just compile it out if I want something a little bit more svelte. So, and there's another example. When I'm working locally and developing, I want like a really nice logger, and I want like verbose logging. In the field, I really don't want this thing to be like, I'm deploying an exploit now. I'm doing something sketchy. Like we don't want that. And we don't want this logging built into the executable itself. So it's really nice to be able to have conditional compiles in here. So I can completely block this stuff out and it's optimized away. And like my debug statements don't end up in the final executable. So Something else that I think is a really nice thing about Rust that I really love is that it has like really powerful macro language that C, like, yeah, there's macros in C. And I thankfully in my career never really got deep into C++. And I know it's a lot more powerful, but Rusts are really easy to use. And so something that I have in here, as I'd mentioned, we want this implant to stay up like hell or high water. We want to do whatever we can to keep it up and try and recover from whatever failures. But like if I'm working locally and I hit a weird bug, sometimes I just want it to panic. And like, so I can see where did this panic originate so I can, fix that issue. Where in production, I'm hoping like, okay, cool. I hit a bug in how I handle like my C2 tracking. I don't want to panic and bail out in production, but in dev, yeah, I do. And I want to see that. So this is just a really quick macro of saying, hey, if this is a debug build, panic. If not, like keep doing what you're doing, try and recover, do whatever you can. So the system itself, we set a lot of stuff up. I have a remote logger. And this is another really, really valuable thing is like, this stuff's going to be out in the field. It's going to be doing stuff. I can't shell in and check on it. I can't like get logs easily from it. So as part of the C2 mechanism, we have this remote logger. We declare it here. This is a pretty simple buffer of just messages. It looks a lot like kind of any logger that you ever used to working with. There's error, warn, info, debug. It's going to pull everything up. We can inject it into whatever method we want. And it's going to get all these logs. And then on a C2 check-in, it's going to phone them back home. So then our attackers can look at it and say, okay, cool. This looks healthy, or there's something going wrong, and help us debug problems in case we need to fix a bug. Because yeah, it's already hard enough debugging a problem, and it's a lot harder when it's like you're debugging a problem on like someone else's computer that you're not supposed to be on. So our state manager, this is where I hold all immutable state for the entire system. And this includes, we generate a, there's going to be a unique UUID for the instance itself. And then we also have pulled out elsewhere a unique UUID of the implant itself. And once again, another nice thing about Rust, there's the build ID crate. So it's like, bam, cool. I have a unique identifier for the build. This is really useful on our side, seeing, if I see from the same IP, the same build, but like a ton of different instance IDs checking in, this is a sign like, hey, maybe this thing's in a reboot loop. Something's wrong with it. Or maybe somehow we have this implant got backed up somehow and rolled out on multiple different images, and they decided to clone it. And now we're seeing all these different unique instance IDs. So it's a helpful practice. I've written it, originally did it for other software. Anywhere where I had something remote in the field that I didn't control, I would always have a unique instance ID because it helped me give just a better idea of what they're doing. And then we pull a lot of stuff out of the configuration that I showed you, and we won't dive into that. A lot of that stuff's pretty boring. Let's go back in. So we have this remote logger. We have our state manager. So we're just going to drop into a simple event loop. And pretty much anywhere we have state or anything that we're going to want to control, I try and inject it. So I can write unit tests and make this stuff really easy to work with and debug. And I really like using the practice of using generics and referencing anything that I want to mock. I use a trait, then I use generics. So then when I do my final build, it's anything related to my dependency injection compiles away. And it saves a lot of space, a lot of performance, and it's really clear and easy to work with. So here we're injecting the state manager, anytime I do unit tests, I just create a new state manager, or I create a new remote logging store. They're really just buffers around a bunch of logs, or where our C2 state is. C2 manager is definitely something that I want to inject. Our C2 manager controls all of our different C2 methods. So in this case, just HTTP, but it's able to handle, as we start adding more, they're all implemented as a trait. So as long as they implement this trait and keep all their state inside themselves, we can just start adding more. And the C2 manager will keep track of, okay, what's our last successful method that we connected with, and what was the last successful C2 server. We're going to stick on that method and destination as long as we can. Once it fails, we're going to rotate to the next one. Pull file contents. You can see this is just a function that accepts a string, which is where the file that we want to pull contents from, and then we're going to have a result of evaluate the contents of the file. Once again, I have this injected so I can test our C2 stuff without actually having to work with the file system itself or deal with any of that. And this is just a main event loop, really boring, just sits there and spins and says, cool, I want to check in, and on my check-in, if I have instructions, I want to do the instructions in order that I got them, and whatever follows up from that. And then finally, after my instructions, we're going to sleep for some callback period. Either my check-in is going to tell me when, or I'm going to have a default, which we saw earlier, which is 5 seconds. So this is another nice thing about Rust. With the pattern matching, I'm able to guarantee in here, I have everything handled. There is the run shell command. Cool, that's covered. I have update config, and then as you see here, this stuff isn't properly implemented yet, so I have those as unimplemented. But if I had just forgotten to include download file, the compiler is going to complain and not let me build. And this gives me a really easy thing to grep for, of saying knowing hey, I still have more work to do. I need to go implement this stuff. So any questions on that stuff so far? Cool. So I will pop over. This is another thing that's kind of a pain about workspaces, and the fact that I had to exclude the implant from the overall workspace is with CLine and IntelliJ, it will not, basically none of the features work on the implant itself, the thing that is excluded from the workspace. It always says files not included into model tree, analysis is not available. So I open the implant itself in one ID, and then I have the rest of the workspace in another. It lets me get work done. It's kind of a pain. I get that I'm doing something weird, so I don't blame them for that not working. So I have a shared library between the two that declares what my protocol looks like and the way it works. And this is another, I just love this about C, that it's really easy to have declarative structures of what something should look like over the wire. And I can just serialize and deserialize it with CERD. So right now I'm doing HTTP and JSON. So that's cool. But later, if I want something else, I can pick a new serialization method, and all of this is still going to stay the same. If I have a new C2 method that doesn't allow me, the body of a post, I can contain a lot of information in it. But if I'm doing something like ICMP, I'm going to need to split this up into chunks. It's still really easy to do, and I'm still going to use the exact same definitions no matter what the method is. I'm just going to serialize the structure, split it up, and send up those individual slices. I may introduce an envelope that declares, this is message 1 of 20, and then it will have the body of these messages. These are also used a lot on server side. So I have a configuration here, say, hey, if the server side helpers are on, I don't want this stuff compiled into my implant itself, but it is really nice to have it on the C2 side. So in this case, it's a library called Validate, which I like love, love, love. If y'all aren't using Validate today, I highly suggest you start using it. It's really powerful. It lets you declare. So in this case, I just say derive validate, and then it will call the validate method on everything that implements it. So in this case, it's going to be log entry, and it's going to look and it's going to see, hey, does this fit whatever validator that we've written for it? Like examples of validators, it comes out of the box with, does this look like a phone number? Does this look like an email address? Is this greater than 0 characters but less than 150? Is it alphanumeric? And it just makes it really, really easy to validate your inputs. And we'll get in later when I start showing you the C2 side, where we can actually force the requirement of validate being called in our router. And so we know anywhere that I have a handler, I know validate's been called, and I know that this input is good, otherwise it's rejected. And it's just like, man, I love that I have that, instead of just like, oh, I need to remember to make sure I validate my input. It's like, no, type system makes me do it. This kind of touches on another thing that I really love about Rust is the doc strings. I mentioned it earlier. In this project, I have deny missing docs turned on, and I'd mentioned something about it, and someone pointed out a way better way to do this is enable warn on missing docs, and then on your CI, fail a build if there's warnings. So that way you're able to work locally. You can move quickly. You don't have to like write a placeholder doc or something like that, or disable this message to get all your work done. But then when it comes time to check it in, if you've forgotten to document anything, it's going to fail to let you check in, which is super nice. So I'd mentioned in here, we have our check-in message, the build ID, which I'd called out, basic UUID, unique to the implant itself, instance ID, and then series of logs, if we have any, saying what's gone wrong, what's going right, whatever I want to send home. Like I mentioned before, this is another thing, just like instance ID. Anytime that I'm writing some client server thing, this is just a default. Day one, I really need to have remote logging available, because like guarantee you're going to find yourself wishing that you had it eventually. Any questions on the protocol itself? Cool. So we had some discussion before this stream started about async await. This is actually my first project that I've used async await on, and I kind of want to use that as an opportunity to learn it. It was still, we'd bought in fairly heavily on a lot of different things at ThreatX before async await got into a place that it was really reliable. We had some low-level MIO or MIO. It's one of those things, you read something on the internet all the time, but like when it comes time to say it out loud, you don't actually know how to say it. Like I didn't know how to say Nginx for the longest. I just never even thought about it, and I was like, oh yeah, I guess that's how you pronounce it. So either MIO or MIO, whatever it is, we had a fair amount of async code written just on that, but none of the async await stuff. So I was like, cool, this is going to be an opportunity for me to learn that and get to play with it. And it's been really nice, and it led me in a direction that I didn't think I was going to go. My default, I picked up Actix for the web server, and I found that dependency injection with Actix was a little bit harder than I thought it would be. And so I played around with a few different frameworks, and I ended up picking up Warp, and it made being able to inject a trait really easy, worked really well. And some of y'all might already be picking up on, there are trouble with using async and traits. And so I'll cover how I handled that. But yeah, I found
the Actix, were you using, which version were you using?
I do not remember. So I started.
Was it the newer one? Because the old one was definitely a pain.
Yeah,
The new one,
it-
not really, not a pain. Just curious.
yeah. How new? Do you know?
Oh, 6, 9 months. It's up to
Mm,
like 3. One was a little bit tougher. You had to
oh,
wrap everything in a actor.
yeah. No, it was probably 3 because I started this in October. So
Yeah,
it
okay,
was.
that's the new stuff. Okay, good.
Yeah, yeah, and like it may have been possible, to be honest. I think if with a little bit more effort, I looked through the bug tracker and I saw enough people complaining about it, and I didn't see any solutions. So like I'll totally be happy to be wrong. And I'm not saying uh I have to say I really like Actix too. Like I know that sometimes the like Reddit bandwagon likes to beat up on it. It's a really nice project. It's really easy to use. We used it for a few things at ThreadX. Um, and yeah, it's just a nice thing. So it didn't work in this case. And also, I'm not trying to make something production worthy. I'm like screwing around in my free time. So I picked up Warp, which is the um, framework from the guy who is doing Hyper. And it's really cool. It's a lot different than anything I'm used to. Like the way the router and the filters work or is it took a little like getting my head around. Um, but once I did, I was like, cool. And I still don't think am using the filters to their full potential. But yeah, so I picked that one up. Let me check my notes on where to go next here. So yeah, I'll actually show how. So something I'm a really strong believer of, once again, is making everything injectable. So any database calls that I have are implemented. We have a DAO implementation, and then there is a trait for it. And so anywhere in the code, we're only ever using the trait, except for one place is initializing the database with initial user. Everywhere else, um, we only reference it through the trait. And so there is a proc macro that exists out there. So apparently there is some hangups in the compiler right now for enabling async and traits. And I don't understand what they are. There's a really interesting blog post about it, of the details of why they don't want to enable this just yet. But luckily there is a proc macro that exists that is basically going to produce what you need boxed up, and you're just going to use it like this was natively supported by the compiler. There's a minor performance overhead, but this is like my C2 side. I don't care. Like, I'm not seeing a ton of traffic on this thing. This thing really didn't even need to be async in the first place. I kind of did it just for fun and to learn. Um, like let's say I implant like 1,000 devices, which is a lot, and they're phoning home once an hour. That's nothing. Like that's like, you know, I have a feeling a few people on here personal blogs get way more traffic than that. So like we're not dealing with heavy traffic here. So I'm not worried about performance overhead. So I don't know. I found that async await async trait proc macro to be super useful, and that's what let me kind of unlock stuff. So in the router itself, everything is declared as we have filters. And this is where I set up my filters. And this stuff is going to look, everything on the C2 side is just going to look like a normal web app, because it totally is. Like, so I'm going to not spend a lot of time here because I don't think this is what a lot of people are here for. But I did want to show one thing. If this is like what I really like about Warp. So I'm going to have a filter for my path. I'm going to require that it's a post. I'm going to extract and validate the body. And then I'm going to require this to happen with a DB. So that is my injected database mock object. with a config. In this case, I need a config so I can generate JOT tokens. We're not going to dive into that. Again, that's not interesting. But this is the interesting part. Anywhere that I have a body, I require it to be extracted by a method like this. And sorry about that. I've got Mac keystrokes stuck in my head. So I've been working in Mac all day. So I have a method here called extract invalidate body. This is going to require some parameter t, and it requires that it send, sync, deserialize, own, and validate. And so we're going to look at the body. I have some arbitrary, I just picked, some limit of how big it should be. It's required to be JSON. And then here, we're going to extract it and validate. Since this is the only path that we have to extract our inputs, I know that if it's been through here and I'm looking at a handler later, it's been through here and it's been validated and it's good. And so then I have to worry a lot less about it. So I think that's really nice. I've got same helper function that exists for the query string. It's almost identical enough that IntelliJ complains to me about duplicate code fragments. And then I do the same thing here with the bearer token. So anywhere that I have an admin API, I add this filter to it, and it's going to extract a JOT claim. It's going to take a config, and basically it's going to pull out the header, and it's going to decode it, and we're going to get what information we need out of it and create a claim. So it's like, this is really nice. So then we go back up. So we're going to look at, once again, this extract validate body. If a header has a body that comes in, that body is added in because of that filter. So I know that it's been validated. So kind of, that's all I've got on that one. I just think it's really cool, and it's a really nice feature of it, where, because I've used a lot of frameworks in the past where, maybe you have like some interpreted languages are really good about letting you provide like an attribute or something like that to a handler, or you're going to have some method that you're going to wrap all your handlers with to check it. But I haven't seen it done with a mix of the router and the type system like that. And I really like that. So I'm going to skip past that because, once again, not super interesting there. One of the things that I do want to talk about, and this is a pattern that I've been using that I've found makes Rust development when you're working with multiple systems a whole lot easier, and is using Docker Compose. And this isn't just Rust. I use this in other languages I work with too. But I want to walk through what I did Rust specific for this to make it work. So I don't know, are people on the call familiar with Docker Compose, or have they used it? Cool. I'm going to give a quick introduction on what it is. So Docker Compose is a higher level wrapper over Docker itself, where you can declare entire networks of multiple services, how they should behave, and the way that they're going to connect to each other. So this lets you, with one command, stand up an entire network and have a pretty decent test environment with oh, I got to start at X, then Y, and I configure this. It's like, no, just get that in your Docker Compose. You're not going to want to use something like this in production, but it is just really nice for like a local development environment. And it requires everything to be Dockerized, but that's really easy to do. And I'm going to show you a couple patterns that make it really easy to do for Rust development systems. So I've got my C2 server declared here. I have a build context. It's going to point to the Docker file I'm going to use. And then pass environmental file variables, just like a 12-factor act. We want this configuration going in there anyways. This is just the way to do it. And so then we're going to look at the Docker file, because that's where a lot of the interesting stuff happens. So I have Docker files for everything that I want. So in here, I have multiple steps. I have my prod build, I have prod, and then dev. So my prod build is actually going to do a release build. And then we will take just a normal Debian build, and we're going to copy over our final artifact from that and then expose it. So now this is going to give us something, a Docker image that we're going to use. And if I build this, this is something that I can deploy out to production. It just has our executable, and if you have any other like dependencies that you need, you can install it in there too, and nothing else. And it's just small and trim. But then I have another layer, which is my development environment. So I am going to copy in my local environment. I'm going to set a work directory, and then I'm going to install Cargo Watch. And then I have a command called wait for it, which says like, okay, cool. I want you to watch Postgres, wait for it to be finished starting. Like, cool, we've got an open socket, and now run Cargo Watch. So that's cool. We have the source code in there, and we have something watching. Cargo Watch lets you rebuild a service anytime anything in the source tree changes. So now the last little thing that we do is we mount a volume. So this mounts my entire workspace in at /app. And so now if I change something locally on my host, that is mapped in as a volume into the Docker container. And so Cargo Watch will see it and rebuild everything. So I do the same thing with the implant. I just want a Docker container. Once again, like when we're deploying this in a compromised system, we're not going to be deploying a Docker container. So like I actually included a prod build in there. I don't know why. It's not necessary, but I think I was just, kind of turning the crank. But here for like just testing, yeah, I'm going to want to stand this up, and I'm going to want to mount this in with the source code in and use Cargo Watch in the same way. So now if I'm working on the implant, it's going to see my changes, it's going to rebuild, and it's going to come back up, and it's going to connect immediately to my C2 server. Or if I'm working on the C2 server, it's going to go down, it's going to make it rebuild and come back up. And so I get like a really quick workflow in working with this whole environment end to end with no fuss, no muss. It declares it the way it should look in production. Yeah, makes it really easy to work with. And then once again, Postgres. So one of the other things, it was something that I bumped into. You can declare something depends on something else. So like my C2 server depends on Postgres, so it's not going to start C2 until Postgres is up. But I had that additional bash script to like watch for the socket to open, because Postgres coming up the first time, like, yeah, the container started, but it's not ready to, like start receiving connections. So I just wanted it to hold off for a little bit until it's ready to go. So like one of the things that I like about this too is it lets me build a self-contained QA environment. And this is something like it's really, really big deal to me, is like quality, quality, quality. And I know I was ranting about it before, but I'm going to rant about it again. Like I think quality and security are like hand in hand. Like exploits, like exploitable bugs are just another class of bugs. And like you're going to find them, like it's a specialized skill to find them. But like a lot of the methods are the same, and the way you prevent them are the same, of having like clean, maintainable, testable code, and being able to introduce new tests as you fix things or discover, like, let's say we have a vulnerability in an upstream dependency that we need to update it. We need to update that, validate it, know that it's good, and be able to release it as quick as we can. So having this automated QA pipeline is like super, super valuable, not just for the quality, but it is a very real security concern. So like this Docker Compose stuff gives me, cool, I have a local QA environment now that's production-ish. And so I use this in my CI pipeline for running smoke tests again. So any functionality that's added in here, so I'm never going to be working with the implant directly. As a user, you're always going to be interacting with the C2 mechanism. So as I add a C2 method, I add a Python file to interact with it and use this stuff. They're pretty simple. It's like, so I really like MyPy for type annotation. Like even when I'm not writing Rust, it still ends up looking kind of rusty just because like I really like type systems. It just makes better code. I don't get why people wouldn't want it. So yeah, each endpoint, I'm going to be introducing a Python test file. The reason why I'm writing this in Python and not in Rust is like forcing yourself to write this in another language often shakes something out, like some kind of assumption that you had somewhere. Like one of the things that I ran into in adding the schedule work endpoint, since all this stuff is being derived from that proto file that I have, like the actual JSON looks super ugly, and it was like kind of a pain to work with in Python. And so, yeah, that called that out. It broke that assumption instead of just relying on these like CERD derive stuff, because then I would just never know how like gross that API is. And once again, there's a lot of different ways to do that. Like in this, I'm using like a shared Rust file to kind of share these protos. There's a lot of other ways to do it. Like, I could actually use like protobufs to generate things, or OpenAPI to generate the client libraries. And then that kind of helps remove this. But those are dependencies that I don't really want inside my implant. So that's one of the reasons why I avoided them, and I ended up writing these by hand. So, but in the end, what we get is so I'll do Docker compose down that tears down my network and deletes any databases that exist. And then we'll do Docker compose up. Actually, I'm going to start a tmux session. Docker compose up. So this is going to bring up our whole network. It's going to go through building it. It's going to take a while. But once I get that up, since I've been going through these effort of as I add these endpoints, I add the Python implementations. I can also, cool, I have a smoke test. This lets me test this from beginning to end of say like, cool, let's implant has checked in. Let's find an ID for it. Let's start scheduling work for it. Let's kick off the work and let's see if we get the results that we expected back. So I have a smoke test, and using the Docker compose stuff, I can really easily run this in my CI. But also, since I went through that effort of writing these Python files, I get a feature for free that I'm going to show you all later. But while that's building, which takes a while, this also goes into another why not Rust. The build times, oh cool, they're done, and it's checking in. Build times are pretty gnarly. So let's see, I think I have, yeah, pip and shell. And so these are debug builds. So debug builds in Rust are just like painfully slow, specifically for the, I believe it's the scrypt implementation is just like so painfully slow. And that's what that long pause is of it initially logging in as a user with admin credentials. And that login takes a while. I'm going to cover some of the CI stuff. Like, I know this stuff is not malware specific. It's just like this is required. No matter what you're writing, being able to have like a good high quality CI pipeline, validates your builds that they're good. It makes everything that you do down the road easier. And like Rust provides a lot of tools that this ended up not being super painful. So I've got 3 builds on it. Also, like I love GitHub Actions. Like they're really nice. They've made a lot of this stuff really easy. It gets kind of expensive with Rust. For a while, my every check-in was it took about 200 billable minutes because of all my cross targets and because OS X is just like super expensive. Once a week, I run cargo audit, check all my dependencies on both the C2 server and the implant side. It says like, hey, do I know of any like bugs in this? Like, do these need to be updated? There's just another basic like software hygiene thing. It's really nice to have. Build the Rust working group on GitHub Actions has done just like a great job. So a lot of this stuff was mostly copy and paste of cool. I run format. I reject any build that I have any format changes on. Run Clippy. Reject anything that Clippy fails. To get back to that problem, where the implant and the C2 are in separate workspaces, each of these actions I have to run on the workspace and the implant separately. But these are all separate jobs and they happen in parallel, which is really nice. So we have a series of unit tests for both the C2 server and the implant. I'd alluded at some of them, didn't dive into them because it's not too interesting. We run them on OS X and Windows for the implant just to see, hey, I want this immediate feedback, like to my unit tests pass. And then on Linux, I actually run a code coverage tool. So I see what my code coverage is and I save that as an artifact. And then do the same thing, C2 server side. That's pretty much it. Oh, and then run MyPy and Flake 8, which are code quality tools for Python on any of my scripts. And then finally, this is all it takes to using that Docker Compose pattern to be able to stand up the server and run all my tests against it. So yeah, that is that. And then now we actually get to we've gone through all of this, the building the implant, building the C2. It's like, cool, all this stuff is there. Like, what can we do with it? So I've got these Python scripts that I've written, and I mentioned that I get a feature for free. So I'm a really big fan of the CMD2 library for Python because it lets you just slam together pretty easy interactive shell for dealing with whatever you want. So now we're going to put ourselves in the headspace of the actual attacker who's using this. This is out there somewhere on someone's network. So first, I am going to want to log in to my C2 server, see what's out there. Often you may have multiple separate like C2 networks that you're using. Like, this is for engagement 1, this is for engagement 2. We don't want them to mix. Like, if the FBI discovers this one, we don't want it to compromise the activity over here. So in this case, it's just on localhost. So this sets which one I'm connected to. I will log in. Once again, this stuff's really easy with Python. Admin, password. Uh-oh. I might have to add the protocol. Yeah, that was it. So this is the long pause. It's the hash of my password and comparing to what's in the database. Long and slow, kind of boring. Oh my gosh, wish you'd hurry up. Cool. So we have one implant checking in. This is the one that you saw in my Docker Compose file. So now we're going to want to connect to it. So before I run this command, I'm going to explain what it does. Is remote shell starts, you saw the work items that I have. Like there's nothing mentioning a shell. It was run commands, it was set config, manipulate files. So what this does is it starts queuing up work because like our implant's not constantly connected. We might have a week until the next check-in time. So I say open a shell. First thing it does is it queues up work of set a configuration file or set the configuration to turn the check-in time to 1 second. So it feels like an interactive shell. This thing's constantly phoning home. I want to start causing trouble. And as I'd mentioned earlier, that might be an operational issue. Like we don't want to get discovered. So you won't want that high callback time. Don't use this shell command. This is if you're a little more brazen and feel like you want to experiment. So I call remote shell, queues up that work. We're waiting for the next implant check-in. Chances are it's probably checked in while I've been blabbing on. So that queues up command, run ls, queues up command with the C2 server, sends a command, say, hey, next implant check-in, which should only be a second away, hand this to it. And then the implant will check in, say, hey, do I have any work? Cool, I have a run command file or run command instruction. It will run just ls and it will look, okay, cool, that's what I have. It will take that output, phone it back home, and display it to me. And then in the background on this, it is just polling to the C2 server. I have a unique work ID for every work that I schedule, saying like, hey, has the implant checked in with like work item 1, 2, 3, 4? No? Okay, I'm going to check again. I'm going to check again until bam, we have our results of LS. And then yeah, it feels you have all that crap going on. Oh, forgot the run command. You have all that crap going back and forth, but you end up having something, oh yeah, this just feels like a shell. Like I don't have to worry about all that like underlying infrastructure. And then we cut back out. And at this point it says, cool, our operator is done with it. Let's set this back on the callback loop that it was on before. So it sets another configuration message. Next check-in, it's going to, cool, I'm going to update my configs. I'm going to go back to checking and every 7 days or whatever the heck it was, and then we're back to normal. So any questions there? Cool. I know it's a big roundabout for basically crappy SSH, but here we are, it works. So what's next? I mentioned file manipulation, port forwarding, mentioned a few times. Add more ICMP. I really want to move this to no STD. Most of the code that I've written, it's going to be pretty easy to do. It's just like kind of a pain in the ass to do it. So I want to start working on some of this stuff. I feel like I have a better grasp, and we've been talking about work, if we want to bring Rust in or not, write an implant in it. Like we already have really good implants in-house that are really powerful. So we might start using one, probably won't be this one, who knows? That's an open topic. Or the next thing on my roadmap is like, I might just like get bored of it and just open source it and drop it on Twitter. So like if you do, there's my Twitter handle, but that's it. That's my full rant.
Awesome. Thanks, Stu. We do have a couple questions. And also if you're on Twitch and you have some questions, go ahead and ask away. So one question that came in a little bit ago is, couldn't the WebSocket be backwards exploitable?
Oh, as in someone could attack the Russian C2 infrastructure?
Maybe if the person, yes, the answer is
okay.
yes.
Absolutely, it can. So it's a really, really real concern here, especially for like a company like where I'm at right now. Like that's a big deal. We we are entrusted, so we're acting as red teamers, and we'll have implants out on customer networks. We're basically like backdoored them. So it's really important that we keep security top notch, where if someone discovers our C2 infrastructure and attacks it, they don't get access to our customer information or the other implants we have. And then also, at the higher level, like international level, where it's GRU versus NSA, which I have no experience in, that is not my world. That's a very real concern that, GRU gets discovered and NSA starts going after them. They're probably gonna have sensitive information in there. So it is of the utmost importance to have the highest quality of code and security practices.
Awesome, thanks. Well, I have another question is, now that you've written this, what would, have you learned like how to prevent this? Like you've written the malware, how to stop your own malware?
That is a good point. So that's like a lot of what my past has been. So like the last thing that I was in was a web application firewall. So we were looking a lot at the signatures of attackers after us. So for actual endpoint security, I haven't given it much mind. So like I have good friends who are in endpoint security, and we've talked a fair amount about it, but I don't think I have anything new and novel to add to that world just yet that I've found out of this.
Awesome, thanks.
Without me.
Does anybody else have any questions?
Oh, okay, I'll be done soon. Yeah, no worries. Cool. Well, I think that was perfect timing because my wife is hungry. So this was super fun. Thank y'all very much for like letting me like rant about this. And if anybody wants like sample code of it, like obviously I can't post the whole thing online. But if people want anything of like the Docker Compose pattern that I was using, I'm like really happy to share that stuff, or like the validate and extract stuff for warp. Happy with that too.
Absolutely. Thank you so much, Stu, again for coming. That was a great presentation. Yeah, I hope that everybody has a great night, and we'll see you all next time, which will be next month.